Electromagnetic induction. Introduction. Electricity and magnetism were considered separate and unrelated phenomena for a long time. In the early decades of the 19th century, experiments on electric current by Ørsted, Ampere and a few others established the fact that electricity and magnetism are interrelated. They found that moving electric charges produce magnetic fields. For example, an electric current deflects a magnetic compass needle placed in its vicinity. This naturally raises the questions like, is the converse effect possible? Can moving magnets produce electric currents? Does the nature permit such a relation between electricity and magnetism? The answer is resounding yes. The experiments of Michael Faraday in England and Joseph Henry in USA, conducted around 1830, demonstrated conclusively that electric currents were induced in closed coils when subjected to changing magnetic fields. In this chapter, we will study the phenomena associated with changing magnetic fields and understand the underlying principles. The phenomenon in which electric current is generated by varying magnetic fields is appropriately called electromagnetic induction. When Faraday first made public his discovery that relative motion between a bar magnet and a wire loop produced a small current in the latter, he was asked, "What is the use of it?" His reply was, "What is the use of a newborn baby?" The phenomenon of electromagnetic induction. Is not merely of theoretical or academic interest but also of practical utility. Imagine a world where there is no electricity, no electric lights, no trains, no telephones and no personal computers. The pioneering experiments of Faraday and Henry have led directly to the development of modern-day generators and transformers. Today's civilization owes its progress to a great extent to the discovery of electromagnetic induction. The experiments of Faraday and Henry. The discovery and understanding of electromagnetic induction are based on a long series of experiments carried out by Faraday and Henry. We shall now describe some of these experiments. Experiment 6.1. Figure 6.1 shows a coil C1 connected to a galvanometer G. When the north pole of a bar magnet is pushed towards the coil, the pointer in the galvanometer deflects, indicating the presence of electric current in the coil. The deflection lasts as long as the bar magnet is in motion. The galvanometer does not show any deflection when the magnet is held stationary. When the magnet is pulled away from the coil, the galvanometer shows deflection in the opposite direction, which indicates reversal of the current's direction. Moreover, when the south pole of the bar magnet is moved towards or away from the coil, the deflections in the galvanometer are opposite to that observed with the north pole for similar movements. Further, the deflection, and hence current, is found to be larger when the magnet is pushed towards or pulled away from the coil faster. Instead, when the bar magnet is held fixed and the coil C1 is moved towards or away from the magnet, the same effects are observed. It shows that it is the relative motion between the magnet and the coil that is responsible for generation, induction, of electric current in the coil. Experiment 6.2. In figure 6.2, the bar magnet is replaced by a second coil C2 connected to a battery. The steady current in the coil C2 produces a steady magnetic field. As coil C2 is moved towards the coil C1, the galvanometer shows a deflection. This indicates that electric current is induced in coil C1. When C2 is moved away, the galvanometer shows a deflection again, but this time in the opposite direction. The deflection lasts as long as coil C2 is in motion. When the coil C2 is held fixed and C1 is moved, the same effects are observed. Again, it is the relative motion between the coils that induces the electric current. Experiment 6.3. The above two experiments involved relative motion between a magnet and a coil and between two coils, respectively. Through another experiment, Faraday showed that this relative motion is not an absolute requirement. Figure 6.3 shows two coils C1 and C2 held stationary. Coil C1 is connected to galvanometer G while the second coil C is connected to a battery through a tapping key K. It is observed that the galvanometer shows a momentary deflection when the tapping key K is pressed. The pointer in the galvanometer returns to zero immediately. If the key is held pressed continuously, there is no deflection in the galvanometer. When the key is released, a momentary deflection is observed again, but in the opposite direction. It is also observed that the deflection increases dramatically when an iron rod is inserted into the coils along their axis. 6.3 Magnetic flux. Faraday's great insight lay in discovering a simple mathematical relation to explain the series of experiments he carried out on electromagnetic induction. However, before we state and appreciate his laws, we must get familiar with the notion of magnetic flux, FIIB. Magnetic flux is defined in the same way as electric flux is defined in Chapter 1. Magnetic flux through a plane of area are placed in a uniform magnetic field B, figure 6.4, can be written as phi B equals B dot A equals BA cos theta, where theta is angle between B and A. The notion of the area as a vector has been discussed earlier in Chapter 1. Equation 6.1 can be extended to curved surfaces and non-uniform fields. If the magnetic field has different magnitudes and directions at various parts of a surface as shown in figure 6.5, then the magnetic flux through the surface is given by the equation 6.2, where all stands for summation over all the area elements dA. Comprising the surface and bi is the magnetic field at the area element di. The SI unit of magnetic flux is Weber, WB, or Tesla meter squared, TM square. Magnetic flux is a scalar quantity. 6.4 Faraday's law of induction. From the experimental observations, Faraday arrived at a conclusion that an EMF is induced in a coil when magnetic flux through the coil changes with time. Experimental observations discussed in section 6.2 can be explained using this concept. The motion of a magnet towards or away from coil C1 in experiment 6.1 and moving a current carrying coil C2 towards or away from coil C1 in experiment 6.2 change the magnetic flux associated with coil C1. The change in magnetic flux induces EMF in coil C1. It was this induced EMF which caused electric current to flow in coil C1 and through the galvanometer. A plausible explanation for the observations of experiment 6.3 is as follows. When the tapping key K is pressed, the current in oil C, and the resulting magnetic field, rises from 0 to a maximum value in a short time. Consequently, the magnetic flux through the neighboring coil C1 also increases. It is the change in magnetic flux through coil C1 that produces an induced EMF in coil C1. When the key is held pressed, current in coil C2 is constant. Therefore, there is no change in the magnetic flux through coil C1 and the current in coil C1 drops to 0. When the key is released, the current in C2 and the resulting magnetic field decreases from the maximum value to 0 in a short time. This results in a decrease in magnetic flux through coil C1 and hence again induces an electric current in coil C1. The common point in all these observations is that the time rate of change of magnetic flux through a circuit induces EMF in it. Faraday stated experimental observations in the form of a law called Faraday's law of electromagnetic induction. The law is stated below. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. Mathematically, the induced EMF is given by the equation 6.3. The negative sign indicates the direction of epsilon and hence the direction of current in a closed loop. This will be discussed in detail in the next section. In the case of a closely wound coil of n turns, change of flux associated with each turn is the same. Therefore, the expression for the total induced EMF is given by the equation 6.4. The induced EMF can be increased by increasing the number of turns n of a closed coil. From equations 6.1 and 6.2, we see that the flux can be varied by changing any one or more of the terms B, A and theta. In experiments 6.1 and 6.2 in section 6.2, the flux is changed by varying B. The flux can also be altered by changing the shape of a coil, that is, by shrinking it or stretching it in a magnetic field, or rotating a coil in a magnetic field such that the angle theta between B and A changes. In these cases too, an EMF is induced in the respective coils.
Here we are using a coil and a magnet. This magnet contains two poles, south pole and the north pole, and in this coil the flow of electrons is also shown. Now if the strength of the magnetic field is about 50%, this will be the magnetic field, and if you want to show the compass, we can click here. Yes, this is the magnetic compass. And if you want to know the magnetic field, we can also use the field meter. So here we can see the magnetic flux along the x-axis, that is in the horizontal plane, and the magnetic field along the y-axis, that's along the vertical plane. And if you want to decrease the strength of the magnetic field, you can decrease like this. And if you want to increase the magnetic field, you can increase like this. And here there is only one loop, and if you want to increase the number of loops, you can do it here. Yes, now the coil has 2 turns, and the loop area is about 50%. We can change this loop area also like this. And the number of loops can be changed like this. And here this is the voltage across the ends of the coil. And the strength, if we are increasing or decreasing like this, this is reflected here. And if you want to lock this magnetic field, that is a magnetic needle, to the axis, you can do like this. So to bring it back to the original condition, yes, this is the thing. And here we can use a bar magnet, and you can also increase or decrease the strength of the magnetic field. We can also change the polarity of the magnet like this. You see the deflection in the compass. Here we can change the voltage supplied to the ends of the coil. Now it is about 10 volts, and you can bring it back to 0 volts. Now no magnetic field. So if you are increasing the voltage, the magnetic field will be changed. If you are having a negative voltage, it will be like this. And the number of loops can also be changed. For this is for 0 volts, and this is for about 10 volts. And the flow of electrons is also shown here along with the compass. Now you have got a transformer, because there is a primary coil and a secondary coil. Here also we can change the voltage or like this. This is alternating current power supply for this coil. So as the direction of the current changes, the magnetic field will also be changed like this. This frequency of the alternating current we can vary like this. Here this is a generator. So here the number of loops can be changed. And so here the magnetic compass is also shown.
Lenz's law and conservation of energy. In 1834, German physicist Heinrich Friedrich Lenz (1804–1865) deduced a rule, known as Lenz's law, which gives the polarity of the induced EMF in a clear and concise fashion. The statement of the law is: the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. The negative sign shown in equation 6.3 represents this effect. We can understand Lenz's law by examining experiment 6.1 in section 6.2.1. In figure 6.1, we see that the north pole of a bar magnet is being pushed towards the closed coil. As the north pole of the bar magnet moves towards the coil, the magnetic flux through the coil increases. Hence, current is induced in the coil in such a direction that it opposes the increase in flux. This is possible only if the current in the coil is in a counterclockwise direction with respect to an observer situated on the side of the magnet. Note that magnetic moment associated with this current has north polarity towards the north pole of the approaching magnet. Similarly, if the north pole of the magnet is being withdrawn from the coil, the magnetic flux through the coil will decrease. To counter this decrease in magnetic flux, the induced current in the coil flows in clockwise direction and its south pole faces the receding north pole of the bar magnet. This would result in an attractive force which opposes the motion of the magnet and the corresponding decrease in flux. What will happen if an open circuit is used in place of the closed loop in the above example? In this case too, an EMF is induced across the open ends of the circuit. The direction of the induced EMF can be found using Lenz's law. Consider figures 6.6, A and B. They provide an easier way to understand the direction of induced currents. Note that the direction shown by A and B indicate the directions of the induced currents. A little reflection on this matter should convince us on the correctness of Lenz's law. Suppose that the induced current was in the direction opposite to the one depicted in Fig. 6.6, A. In that case, the south pole due to the induced current will face the approaching north pole of the magnet. The bar magnet will then be attracted towards the coil at an ever-increasing acceleration. A gentle push on the magnet will initiate the process and its velocity and kinetic energy will continuously increase without expending any energy. If this can happen, one could construct a perpetual motion machine by a suitable arrangement. This violates the law of conservation of energy and hence cannot happen. Now consider the correct case shown in Fig. 6.6, A. In this situation, the bar magnet experiences a repulsive force due to the induced current. Therefore, a person has to do work in moving the magnet. Where does the energy spent by the person go? This energy is dissipated by Joule heating produced by the induced current. Motional electromotive force. Let us consider a straight conductor moving in a uniform and time-independent magnetic field. Figure 6.10 shows a rectangular conductor PQRS in which the conductor PQ is free to move. The rod PQ is moved towards the left with a constant velocity v as shown in the figure. Assume that there is no loss of energy due to friction. PQRS forms a closed circuit enclosing an area that changes as PQ moves. It is placed in a uniform magnetic field B which is perpendicular to the plane of this system. If the length RQ equals x and RS equals L, the magnetic flux phi B enclosed by the loop PQRS will be as follows. Since x is changing with time, the rate of change of flux phi B will induce an EMF given by the equation 6.5. Where we have used dx by dt equals minus v, which is the speed of the conductor PQ. The induced EMF BLV is called motional EMF. Thus, we are able to produce induced EMF by moving a conductor instead of varying the magnetic field, that is, by changing the magnetic flux enclosed by the circuit. It is also possible to explain the motional EMF expression in equation 6.5 by invoking the Lorentz force acting on the free charge carriers of conductor PQ. Consider any arbitrary charge Q in the conductor PQ. When the rod moves with speed v, the charge will also be moving with speed v in the magnetic field B. The Lorentz force on this charge is QVB in magnitude, and its direction is towards Q. All charges experience the same force, in magnitude and direction, irrespective of their position in the rod PQ. The work done in moving the charge from P to Q is W equals QVBL. Since EMF is the work done per unit charge, epsilon equals W by Q equals BLV. This equation gives EMF induced across the rod PQ and is identical to equation 6.5. We stress that our presentation is not wholly rigorous, but it does help us to understand the basis of Faraday's law when the conductor is moving in a uniform and time-independent magnetic field. On the other hand, it is not obvious how an EMF is induced when a conductor is stationary and the magnetic field is changing, a fact which Faraday verified by numerous experiments. In the case of a stationary conductor, the force on its charges is given by F equals Q, E plus V cross B equals QE. Since V equals 0, thus, any force on the charge must arise from the electric field term E alone. Therefore, to explain the existence of induced EMF or induced current, we must assume that a time-varying magnetic field generates an electric field. However, we hasten to add that electric fields produced by static electric charges have properties different from those produced by time-varying magnetic fields. In Chapter 4, we learnt that charges in motion, current, can exert force, torque on a stationary magnet. Conversely, a bar magnet in motion, or more generally, a changing magnetic field, can exert a force on the stationary charge. This is the fundamental significance of the Faraday's discovery. Electricity and magnetism are related. Inductance. An electric current can be induced in a coil by flux change produced by another coil in its vicinity or flux change produced by the same coil. These two situations are described separately in the next two subsections. However, in both the cases, the flux through a coil is proportional to the current. That is, phi b proportional to I. Further, if the geometry of the coil does not vary with time, then dFIB by dt is proportional to di by dt. For a closely wound coil of n turns, the same magnetic flux is linked with all the turns. When the flux phi b through the coil changes, each turn contributes to the induced EMF. Therefore, a term called flux linkage is used which is equal to n phi b for a closely wound coil, and in such a case, n phi b is directly proportional to I. The constant of proportionality, in this relation, is called inductance. We shall see that inductance depends only on the geometry of the coil and intrinsic material properties. This aspect is akin to capacitance, which for a parallel plate capacitor depends on the plate area and plate separation, geometry, and the dielectric constant K of the intervening medium, intrinsic material property. Inductance is a scalar quantity. It has the dimensions of ml square t power minus a power minus2, given by the dimensions of flux divided by the dimensions of current. The SI unit of inductance is Henry and is denoted by H. It is named in honor of Joseph Henry, who discovered electromagnetic induction in USA, independently of Faraday in England. Mutual inductance. Consider figure 6.12, which shows two long coaxial solenoids each of length L. We denote the radius of the inner solenoid S1 by R1 and the number of turns per unit length by N1. The corresponding quantities for the outer solenoid S2 are R2 and N2, respectively. Let N1 and N2 be the total number of turns of coils S1 and S2, respectively.
When a current I2 is set up through S2, it in turn sets up a magnetic flux through S1. Let us denote it by phi1. The corresponding flux linkage with the solenoid S1 is given by the equation N1 phi1 is equal to M12 I2. M12 is called the mutual inductance of the solenoid S1 with respect to the solenoid S2. It is also referred to as the coefficient of mutual induction. For these simple coaxial solenoids, it is possible to calculate M12. The magnetic field due to the current I2 in S2 is mu0 N2 I2. The resulting flux linkage with the coil S1 is N1 phi1 is equal to N1L into pi R1 square into mu0 N2 I2, and that's given by mu0 N1 N2 pi R1 square L I2, where N1L is the total number of turns in the solenoid S1. Thus, from the equation 6.7 and 6.8, we have M12 is equal to mu0 N1 N2 pi R1 square L. Note that we neglected the edge effects and considered the magnetic field mu0 N2 I2 to be uniform throughout the length and width of the solenoid S2. This is a good approximation, keeping in mind that the solenoid is long, implying L is very much greater than R2. We now consider the reverse case. A current I1 is passed through the solenoid S1 and the flux linkage with the coil S2 is given by N2 pi 2 equal to M21 I1, where M21 is called the mutual inductance of the solenoid S2 with respect to the solenoid S1. The flux due to the current I1 in S1 can be assumed to be confined solely inside S1 since the solenoids are very long. Thus, flux linkage with the solenoid S2 is given by N2 pi 2 equal to N2L into pi Rn square into mu naught N1 I1, where N2L is the total number of turns of S2. So we have M21 is equal to mu naught N1 N2 pi R1 square L. So in equation 6.9 and equation 6.10 we get M12 equal to M21 that's equal to M. Thus, we have demonstrated this equality for long coaxial solenoids. However, the relation is far more general. Note that if the inner solenoid was much shorter than and placed well inside the outer solenoid, then we could still have calculated the flux linkage N1 pi 1 because the inner solenoid is effectively immersed in a uniform magnetic field due to the outer solenoid. In this case, the calculation of M12 would be easy. However, it would be extremely difficult to calculate the flux linkage with the outer solenoid as a magnetic field due to the inner solenoid would vary across the length as well as cross-section of the outer solenoid. Therefore, the calculation of M21 would also be extremely difficult in this case. The equality M12 is equal to M21 is very much useful in such situations.
We explained the above example with air as the medium within the solenoids. Instead, if a medium of relative permeability R had been present, the mutual inductance would be as given below. It is also important to know that the mutual inductance of a pair of coils, solenoids, etc., depends on their separation as well as their relative orientation. Now, let us recollect experiment 6.3 in section 6.2. In that experiment, EMF is induced in coil C1 wherever there was any change in current through coil C2. Let phi1 be the flux through coil C1, say of N1 turns, when current in coil C2 is I2. Then, from equation 6.7, we have N1 phi1 equals Mi2. For currents varying with time, d by dt of N1 phi1 equals d by dt of Mi2. Since induced EMF in coil C1 is given by epsilon 1 equals minus d by dt of N1 phi1, we get epsilon equals minus m di 2 by dt. It shows that varying current in a coil can induce EMF in a neighboring coil. The magnitude of the induced EMF depends upon the rate of change of current and mutual inductance of the two coils. Self-inductance. In the previous subsection, we considered the flux in one solenoid due to the current in the other. It is also possible that EMF is induced in a single isolated coil due to change of flux through the coil by means of varying the current through the same coil. This phenomenon is called self-induction. In this case, flux linkage through a coil of N turns is proportional to the current through the coil and is expressed as equation 6.13, where constant of proportionality L is called self-inductance of the coil. It is also called the coefficient of self-induction of the coil. When the current is varied, the flux linked with the coil also changes and an EMF is induced in the coil. Using equation 6.13, the induced EMF is given by 6.14. Thus, the self-induced EMF always opposes any change, increase or decrease, of current in the coil. It is possible to calculate the self-inductance for circuits with simple geometries. Let us calculate the self-inductance of a long solenoid of cross-sectional area A and length L, having N turns per unit length. The magnetic field due to a current I flowing in the solenoid is B equals mu naught Ni, neglecting edge effects, as before. The total flux linked with the solenoid is mu naught N square ALI, where NL is the total number of turns. Thus, the self-inductance is given by the equation 6.15. If we fill the inside of the solenoid with a material of relative permeability mu R, for example soft iron, which has a high value of relative permeability, then we get the equation 6.16. The self-inductance of the coil depends on its geometry and on the permeability of the medium. The self-induced EMF is also called the back EMF as it opposes any change in the current in a circuit. Physically, the self-inductance plays the role of inertia. It is the electromagnetic analog of mass in mechanics. So, work needs to be done against the back EMF, epsilon, in establishing the current. This work done is stored as magnetic potential energy. For the current I at an instant in a circuit, the rate of work done is as given below. If we ignore the resistive losses and consider only inductive effect, then using equation 6.14, the rate of work done is as given below. Total amount of work done in establishing the current I is given by the following equation. Thus, the energy required to build up the current I is given by the equation 6.17. This expression reminds us of mv squared by 2 for the mechanical kinetic energy of a particle of mass m, and shows that L is analogous to m, that is, L is electrical inertia and opposes growth and decay of current in the circuit. Consider the general case of currents flowing simultaneously in two nearby coils. The flux linked with one coil will be the sum of two fluxes which exist independently. Equation 6.7 would be modified into M1 phi1 equals M11 I1 plus M12 I2, where M11 represents inductance due to the same coil. Therefore, using Faraday's law, we get the following equation. M11 is the self-inductance and is written as L1. Therefore, the EMF is given by the following equation. AC generator. The phenomenon of electromagnetic induction has been technologically exploited in many ways. An exceptionally important application is the generation of alternating currents, AC. The modern AC generator with a typical output capacity of 100 megawatts is a highly evolved machine. In this section, we shall describe the basic principles behind this machine. The Yugoslav inventor Nikola Tesla is credited with the development of the machine. As was pointed out in section 6.3, one method to induce an EMF or current in a loop is through a change in the loop's orientation or a change in its effective area. As the coil rotates in a magnetic field B, the effective area of the loop, the face perpendicular to the field, is a cos theta where theta is the angle between A and B. This method of producing a flux change is the principle of operation of a simple AC generator. An AC generator converts mechanical energy into electrical energy. The basic elements of an AC generator are shown in figure 6.13. It consists of a coil mounted on a rotor shaft. The axis of rotation of the coil is perpendicular to the direction of the magnetic field. The coil, called armature, is mechanically rotated in the uniform magnetic field by some external means. The rotation of the coil causes the magnetic flux through it to change, so an EMF is induced in the coil. The ends of the coil are connected to an external circuit by means of slip rings and brushes. When the coil is rotated with a constant angular speed omega, the angle theta between the magnetic field vector B and the area vector A of the coil at any instant t is theta equals omega t, assuming theta equals 0 degree at t equals 0. As a result, the effective area of the coil exposed to the magnetic field lines changes with time, and from equation 6.1, the flux at any time t is phi b equals Ba cos theta equals Ba cos omega t. From Faraday's law, the induced EMF for the rotating coil of n turns is then given by the equation 6.19, where NBA omega is the maximum value of the EMF, which occurs when sin omega t equals plus or minus 1. If we denote NBA omega as epsilon naught, then we get the equation 6.20. Since the value of the sign function varies between plus 1 and minus 1, the sign, or polarity of the EMF changes with time. Note from figure 6.14 that the EMF has its extremum value when theta equals 90 degree or theta equals 270 degrees, as the change of flux is greatest at these points. The direction of the current changes periodically and therefore the current is called alternating current, AC. Since omega equals 2 pi nu, equation 6.20 can be written as equation 6.21 where nu is the frequency of revolution of the generator's coil. Note that equation 6.20 and 6.21 give the instantaneous value of the EMF and varies between plus epsilon naught and minus epsilon naught periodically. We shall learn how to determine the time average value for the alternating voltage and current in the next chapter. In commercial generators, the mechanical energy required for rotation of the armature is provided by water falling from a height, for example, from dams. These are called hydroelectric generators. Alternatively, water is heated to produce steam using coal or other sources. The steam at high pressure produces the rotation of the armature. These are called thermal generators. Instead of coal, if a nuclear fuel is used, we get nuclear power generators. Modern-day generators produce electric power as high as 500 megawatts, that is, one can light up 5,100,000 watts bulbs. In most generators, the coils are held stationary and it is the electromagnets which are rotated. The frequency of rotation is 50 Hz in India. In certain countries such as USA, it is 60 Hz.